Okay, so welcome to the sixth class of Emerging Technologies for Lifelong Learning. Today, we'll be going over the introduction to quantum computing. Now, quantum computing is truly an emerging technology area. It's fast developing. Various people in the industry and investment community, they kind of like jockeying for position to be a future dominant player in this space. If I were to characterize, I guess sort of like the, wait, I don't need this, hold on. If I were to characterize where we are with respect to the, technologies S-curve, so to speak, this is a bit very, very early. Okay, so it's not quite like AI. In fact, it's not even comparable to AI 20 years ago. I mean, AI 20 years ago probably was a lot more on a firmer footing than quantum computing. So quantum computing is very early. Having said that, again, it's something that's going to be relevant for your future. Yeah, definitely. So my game plan is to, well, for you to understand basically the gist of how quantum computing works, okay? And for that, you have to understand a little bit about, how classical or what we call digital computing works. I mean, you know how to use them, but you need to know a little bit how, from the ground up, starting from individual electronic bit, binary unit of information, builds all the way up to application. And then we'll go to qubit, which is a quantum analog of a regular digital bit, binary computer bit that you're familiar with. And then we start to understand a little bit about quantum computing algorithm. How do you sort of work with quantum computer? You don't have a general programming language in quantum quite yet. Well, you do have an interface top level of it, but in terms of actual functionality, it's not a general purpose. It's not like a digital computing where you can program it to calculate anything. And then we'll go focus into the quantum computing application. Okay, but first let me just backtrack a little bit. And here I was hoping to use the paper presentation. Hoping to write. Where did the guys go? Okay, so first thing you need to know a little bit, at least, is the baseline of what quantum physics is all about. Okay, quantum physics. Well, the first word you need to know is quantum mechanics. Okay, now in physics, mechanics is about the mathematics, really, of how you model physical movement or interaction. Okay, now in classical physics, you can think of, in high school, you talk about this billiard ball, right? So they're like, you have two billiard ball coming in, one has this momentum, the other one has that momentum, they hit each other, they bounce off, and there's a conservation of momentum, there's a conservation of energy. So on the one hand, you study kinematics, which is, the position, velocity, speed, acceleration, right? On the other hand, you have dynamical equation, and that means you have force, right? Like gravity, okay? And so forth, attraction, the Newton's inverse square law and so forth. These are the sort of like the energy that kind of like powers the interaction or the movement and so forth, okay? And that's basically the physics of everything we see, from the scale that you can identify with, which is like you, yourself, an apple, an orange, a billiard ball, all the way to celestial mechanics, which means the size of the stars, all the way upward. Okay. And it also works on something much smaller than you can see, perhaps with the naked eyes. But once you get to the lowest level, very tiny, 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 tiny level, right? A few atoms, like we talked about last week, of nanoscale, okay? We also have law of motion, of how things move, how things interact, okay? Except the rules are a little bit funny, okay? Now, the first thing I need you to understand is, well, hold on. The first thing I need you to understand is, well, the word quantum itself, okay? The word quantum. So before we go to it, so I'm just gonna give you a sort of like, I guess, hand-waving story of what quantum mechanics is all about for about 5 minutes or so, okay? Before we go to quantum computing. Well, first of all, the word quantum is derived from quanta, or, quantity, okay? It literally means quantity. Okay? Quantum just comes from the word quantity. Now, what does that quantity means? It's kind of like, I have to go back to the history a little bit. Okay. I guess about 100-ish, maybe 120 years ago, if you shine a light, right? If you shine light on surface, metal surface, then it kind of like absorbs the energy from the light and then emits it back in the form of radiation. Okay. Now, common sense would be something like, well, if you shine the light of this energy, the resulting emission should have that energy or something like that, okay? And if you shine the light that's twice as energetic, hey, maybe, so like twice as intense, right? Maybe you should get twice as much energy out. Well, it turns out it doesn't. It doesn't, okay? So if you go to internet, yeah, let's go with internet, we can. Do you want to allow this app to make sure? No, we don't have to update. Okay. What did Einstein win Nobel Prize for? Okay. You might be surprised to know that he actually didn't win it for relativity. Okay. He didn't win it for relativity. Okay. We can go to here, I guess. What did he, accept all cookies? Yeah, where is that? Where is that? No, it's too much trivia. Okay. I'm looking for this word in particular. This word, photoelectric effect. Okay. This word I'm looking for. Okay. He actually didn't win the Nobel Prize for special or general relativity, which is what he became identified with. Very well known for that. One of the reasons is because the experimental evidence wasn't available to prove relativity for quite some time, I guess. But what was proven and what he got the Nobel Prize for was his theory of photoelectric effect. Okay. Now, what it means is exactly what I was describing. Photo means light. Okay. So you shine light and you get this kind of electron emission that result from it. Well, so yeah, you can read here. Phenomenon in which electrons are emitted from the surface of metal. It's usually metal, so it doesn't always have to be metal, when light shines on it. Okay. So common sense would say that if you shine really intense light, you get a lot more energy. Well, it turns out that the energy of the emission is actually proportional to the frequency of the light that's shining on it. Okay, it's proportional to the frequency. Okay, so that's a big deal. That's a big deal. The other big deal is the fact that the energy doesn't vary continuously. Again, because it's a multiple of, it's some kind of, multiplied to a frequency, it's discrete. In other words, there's a level of energy that you get, and you don't get just a little bit more energy. Okay, as you change the frequency, you have to, once you change the frequency, the energy change, but it doesn't change continuously. It's a little bit higher energy, a little bit higher. It actually jumps in level. It's like a ladder. Okay, so think of a ladder versus ramp. Ramp, you can sort of like crawl up the slope to gain a little bit elevation, but with stair, you jump in elevation 20 centimeters at a time. Okay. Likewise, this photoelectric effect, the light increase in energy in discrete jumps. Okay, and that was not understood. Nobody could understand it. Nobody could explain it. And this photoelectric effect that Einstein won the Nobel Prize for, account for that. It's like multiple jumps. Okay, it jumps in accordance with the frequency, and so it's discrete jump. So the word quanta or quantum in quantum physics refer to the fact that the energy jumps in step. Okay, so quanta in this case just means step. So energy doesn't go up continuously, it goes up in step, discrete step. And those steps are called quanta. Okay, and the physics that's based on that, again, this is interaction at the very tiny level, right? We're talking about electronic being emitted from a surface. So this is not billiard balls being emitted. These are individual electrons being emitted. So we talked about very tiny, even smaller than the nanoscale. This is getting to atomic scale, right? So anyway, so that's where the word quantum comes from. See, okay, there it is. That's the word quanta. Okay, so so you can think of it as, well, in that case, the light itself is not some kind of continuous quantity. It's like a little packet of energy, right? And you have discrete packet, just like you don't have like continuous amount of ketchup. You have packet of ketchup, right? One packet of ketchup, two packets of ketchup, three packets of ketchup. You don't have continuous variation in the volume of ketchup. So you can think of light as like packet of ketchup. So you can only get one packet, two packet, 3, 4, 5. You can't get 1.5 packet. Okay, and those packets are called quanta. Okay, and that basically was the basis of quantum mechanics. Okay, so what this means is that fundamentally at the lowest level, energy is quantized. And that became the basis for the quantum mechanics and quantum physics. Energy is quantized, comes in packet of ketchup, not a bottle where you can pour as much as you can, but in little packets of ketchup. Okay, fine. So yeah, okay, that's the name of the paper on the heuristic view. Okay, so that's okay. So that's enough of a history for that. The point is, you need to understand that that's where the word quantum physics come from. Okay, quanta or quantum. Second thing you need to understand, and can I use the paper now, or okay, good. I was kind of like stalling for time for you to come and switch the screen. I'm much happier because now we can switch. Let's go switch the screen, and yeah, why don't you sit very close so we can. So how do I do this? I go to here. Well, okay, I'll let you do it. We'll stop the screen check. Okay, fine. Oh, stop share here first. Fine. Okay. Right. It's much better. Okay. Oops. Cannot. Can't call them again, I guess. Okay, switch back, switch back. Holy cow. Not happy. Okay. ได้จ้ะได้จ้ะ Share screen. How? Oh boy. You have to edit this part out. Yes, it's all nonsense. Let me try this. Let me try paint. Okay, let's see if it works. I don't know if that's gonna work. Okay, let's get a big line. And let's make it wavy. Okay. Oh boy. Pen. Okay. Right. Okay. So everybody look at the screen. I'm trying to do my best to draw this this thing. Okay. I'm just gonna draw something arbitrary. Make it bigger. Okay. Okay. This is some function. Okay. Think of this as x. This is kind of like space. Okay. So let's live on a one-dimensional space. Right? One-dimensional space. Okay. Now, here's what happened. With physics, okay, classical physics, okay, look at the screen. When I talk about a particle moving, it's basically, a particle that goes here and then moves to the right with some velocity or moves to the left, okay? And then it can accelerate, whatever, okay? Just go back and forth. It's actually a point, okay? So when you think of a billiard ball, we're actually thinking of the center of the billiard ball, so the center of mass moving, okay? Fine. Now, imagine first that you have a kind of like blurry idea of where the particle is. So instead of having a particle, you have a wave function. Sorry, forget the word I said. You have a probability distribution, okay? So this is kind of like where that ball could be. So instead of this particle being a point moving, if you think about this, it would be something like this distribution is kind of like moving to the right. Okay, so you're not quite sure where the particle is, but it's kind of around there. Okay, so when we talk about particle moving to the right, it's the distribution of its location moving to the right. Okay, so first of all, that's as close as accurate as you're going to get. At the very tiny level, atomic level, quantum level, you can't be sure where the thing is. You kind of like, you can be sure of where it is roughly. Okay, so there's kind of like uncertainty. So when we model the movement, we don't say this point moves to the right. You say this probability moves to the right. Okay, now, just like the particle in physics, in classical physics, move according to differential equation, right? Right? I don't. You need reminded. Hopefully, you don't need reminded about that. Let's say you have acceleration being due to gravity, right? And acceleration is the second derivative of the position. The first derivative of the position is the velocity and so forth, right? So you have differential equation that governs the movement of the point. Likewise, you need differential equation here, okay? So you would think it's a differential equation that governs maybe the mean of this distribution. Well, it turns out that that's not how it works. It's more complicated than that. First of all, I'm going to erase everything and I'll show you something else. Let's say something like this. Notice I put some negative there. Okay, so obviously this cannot be probability distribution, right? Probability distribution cannot be negative, right? This is actually what's called wave equation, psi. Okay, this is psi of x. This is actually the analog of a point. Okay, in classical physics, you have billiards moving, right? So that is, you work on actual position x itself. Here, you don't. You work with this funny thing called phi of x, called the wave function. The thing is, once you square it, okay, once you square it, so in other words, you get something like this, right? Right? This is actually the probability of the location of the particle, the one that I was telling you about. Okay, so in other words, let me draw another one. Escape, undo. Okay. The picture that I was showing you earlier about this particle moving to the right, okay, actually, in terms of the function itself, there's an underlying wave function that actually moves. So this function could be negative, right? Because when you square it, you can get this as well, right? Right? Okay, so you don't model the motion of a point. You model the motion of this thing, which could be negative, but once you square it, it becomes PDF, basically. Okay, so the second thing you need to know is that this is how quantum mechanics work. That's why sometimes you hear the word wave mechanics, because instead of a point mechanic, as in billiard ball moving, you have wave equation or wave function. This guy, this black guy. Okay, so this black guy, oops, is phi, and this thing is phi square, basically. Okay. Okay. So does that make sense? Does that make sense? Okay. Now, just like in probability theory or probability class, you have PDF, and PMF, right? So you have the difference between, say something like, so this is a PDF and this is a PMF, right? Right? Okay. So this is not discrete, this is discrete. Today, we are going to work with the discrete version. So what it means is that if this is a probability, this is also a probability function, right? This came from a square. This also came from a square. So the underlying wave function could be something like negative and square root of that, or maybe positive. Okay. So just as this guy have underlying, which could be negative, but then you take square, it becomes a positive, so to speak. Okay. I'm kind of like making a very dirty analogy, but you get the point. Okay. Basically, I write it here just to show that you need to sort of like square it to make it positive. Likewise, you can think of this black line here as my wave function. Because after all, it's something that when you take the square, it gives you the probability distribution, right? You square this black one, you get this blue, you square this black one, you get this blue, you square this black one, you get this blue, you square this black one, you get this blue. Okay, does that make sense? Okay, so the principle of quantum mechanics kind of like work on the wave function that you have to square to get the probability. Today, we are going to work with quantum computing, which means that the underlying will be working with something on more akin to the right picture. Okay. So that's the picture. Okay. Now, So, oops. Right. I'll come back to this. I'll come back to this. Don't need to save this. Okay. Right. And just as you can have the quantum description of an electron as a wave function, so when the electron moves to the right, it's the wave function that moves to the right, and the square of that is the probability distribution of the location of the electron moving to the right, okay? Now, we're not talking about the wave function of an electron. We're talking about wave function of a binary digit. And that's the basis of quantum computing. Okay. So now we start the lecture proper. Okay. Now this is, I'll give you this so you don't have to write down, but every word here is very important. Classical computing, in which case I actually mean digital computing, okay? But if you study history of science, the digital part only came in the last century. There was computing before that, and they used something like mechanical gear and stuff like that. So it's quite interesting. Anyway, so classical computing is a science and engineering discipline, okay, that, why is this unstable? Uses binary digit, and this is called bit. Binary digits, B-I-T, you cut B-I from binary, digit T. So basically it's B-I here plus T over here. So that's the bit, okay? So the bit is a binary digit, okay? That's manipulated. So binary digit, okay? Right now, I can just tell you binary digit is something that I actually is number 1 or number 0. It's something that has 2 states, head or tail, boy or girl, big or small, just 2 states, right? So it's going to be 1 and 0. Those are the 2 possible states, okay? Right. And this possible state can be manipulated. What do I mean by manipulated? It means, well, first of all, you can leave it be or you can flip it. You can set it, you can flip it. Okay? So basically you have something that always say set everything to 1, set everything to 0, or if I'm given a 1, give back 0. If you give me a 0, I give you back 1. It's that kind of manipulation. Now that's not interesting because that's 1 bit, right? The interesting part comes because you're manipulating more than 1 bit, okay? In fact, your computer right now is based on gazillion bits. That's why life is interesting, right? If it's only manipulates 0 and 1, can't do much. Okay. That manipulation is done through what's called logic gate. Okay, and I'll tell you a little bit about what logic gate is. Okay, these are the components. Now, right now, both the digit itself, the 0 and 1 state, and the manipulate, turning 1 to 0 or turning 0 to 1 or whatever, right, is performed using electrical circuit. Okay, and that's where your chip comes in, right? Your chip is basically an array of transistor, right? Tiny pieces of transistor. Well, a transistor is one of those things that can be 1 or 0, so it keeps binary state. So your chip is actually an array of gazillion of silicon bit. Okay, so let's try that. Let's try that. Yeah. Okay, I'll keep talking while you try this thing. Perhaps na look. Yeah, we can edit it. Did you guys do physics in high school? Actually, to be honest with you, quantum computing right now is only understood at graduate student level. There's no like intro to quantum computing courses there. So let's see. Maybe ask what you think. I mean, I can sort of make this into a proper course. Introduction to as far as the classes like that. But I don't know if it's that's worth my effort. I think that's something that I could do, should do as a native course because it's combines elementary understanding with the technology, and the Department of Mathematics or Computing won't do it properly because they just keep quantum computing for graduate students, advanced computing students. But it's not that much math, it's linear algebra. Yeah, actually, to be honest with you, a lot of this is just linear algebra. Not the kind of linear algebra that you have studied. It's a slightly turbocharged version of it, but it's still linear algebra. Now we can give up. Oh, okay, let's give them a few minutes to try out. If not, we'll just give up and go back to yeah, go. Not very much.เนี่ยมันน่าจะเป็นที่สายอะไรแบบอย่างดึงเข้าดึงออกเพราะว่าอันนี้มันก็ต่อติดแต่ว่ามันไม่ยอมไปโผล่อย่างนี้ห้องอื่นเป็นไหมห้องอื่นนี่มันน่าต้องสายที่มาเปลี่ยนยอมแพ้ดิวันนี้ยอมแพ้ไปกันติดหมดเลย It's not working. Not working. That's not working. Yeah, it doesn't work. Okay. ยอมแพ้ยอมแพ้ไอ้นี่ก็ยังเหมือนเดิมนะดังๆเบาๆไม่หรอกอันนี้ก็ไม่รู้เป็นห้องนี้หรือว่าต้องเปลี่ยนห้องบ้างไหมห้องนี้มันรู้สึกไม่ได้เรื่องเลยเนี่ยเดี๋ยวดังเดี๋ยวเบาเดี๋ยวเบาเดี๋ยวดังฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโหลฮัลโห เห็นไหมแล้วอยู่ๆมันก็ดังบุ้งขึ้นมาแต่เนี้ยมันไม่ดังอันนี้ไม่ค่อยดังแต่เดี๋ยวมันก็ตูมขึ้นมาช่างมัน very steep. Hello.
ปกติใช่ไหม
ไม่มันโอเคแล้วเดี๋ยวมันจะดังกว่านี้เยอะเลยไปช่างมันโอเคเอาตอนเนี้ยเท่าไหร่ พิการจริงๆจากว่าไม่รู้ว่างๆมีเวลาว่างก็ช่วยมาดูหน่อยแล้วกันถ้าดูแล้วห้องอื่นไม่เป็นเนี่ยเทสไอ้เนี่ยสลับไปสลับมาถ้าห้องอื่นไม่เป็นก็สลับห้องให้ผมนะ
เดี๋ยวผม
เออช่างมันว่างๆเราจัดการให้หน่อย Okay, we'll kind of edit back to right. Okay, so right now, virtually all the computing is done on silicon chips. Okay, basically that means the silicon chip, which is like an array of bits or 1 or 0, that's manipulated through circuitry that manipulates the 0 and 1. That's what it means, right? What it does is we kind of like map the 0 and 1 into variable, into sort of operations like assigning the value, erasing the value, taking the value, adding, subtraction. So basically all the computational or information processing is then mapped onto this logic gate manipulation. Okay, and that's why you build this kind of layer of abstraction. And so what happened is you take advantage of this computer programming hierarchy. What I mean by hierarchy is that the most basic level of computer programming is literally manipulating the 0 and 1, right? Sometimes you go to, you have a friend in computer engineering, they talk about assembly language, okay? That's sort of like a very low level of language where you are practically, converting 0 to 1 and 1 to 0. Maybe not that primitive, but anyway, you have this hierarchy of abstraction into a higher and higher and higher and higher and higher level, into general level language, like, say Python, to something even more decorative, again, like Wolfram Mathematica, and now you can think of ChatGPT as another layer of computer programming, okay, where you program by English sentence request, and then the ChatGPT turns this into a Python or code or whatever, and then execute it for you, okay? And it develops kind of like computational tasks or application that mechanical computing cannot do. In other words, if you think of mechanical, it's you go to an antique store, maybe you will see a calculator that's kind of like almost electromechanical, and all it does is just add and subtract. You can't do anything more elaborate than that. So there isn't a hierarchy of computer program, okay? But with classical computing, there's a hierarchy of computer program. So that's what classical computing is, okay? Now, quantum computing, you have to realize that quantum computing, and I hope this is well known by now, but when I was giving this talk, I think back in 2018, there was a lot of misconception then, so I might as well repeat it just in case. Quantum computing is not same kind of computing with a lot more power. Okay, it's not like a turbocharged computer. Okay, it's not like taking the computer that you have in front of you right now and bless it with the power of quantum or something like that. It's not. Okay, it's not an old paradigm. It's an entirely new thing. And on the slides here, I show you something else which is kind of curious. Actually, you might want to look it up. It's called DNA computing. It's also one of those things where it's completely new paradigm of computing. Okay, it's called DNA computing. Okay? But that technology kind of like has not really has kind of fallen out of favor a little bit. So you can imagine that you have classical computing, and you have quantum computing, and you have DNA computing, and you have a startup company that invests in DNA computing, another one that invests in developing the quantum computing technology. Okay. So what's quantum computing? Okay. Likewise, now I keep this sentence here, so when you go study your note, you can see that I keep the same sentence structure. It's also a science and engineering discipline, okay? That's also used in bit, But instead of using just regular 0, 1 bit, it uses quantum mechanical bit. Okay? And I add the word entangle a little bit. You don't have to understand what it is, but anyway, it's just a different kind of bit. Because it's very different kind of bit, okay? It may not be implemented on the same digital chip. In fact, it most likely isn't, okay? Just like a transistor can implement 0 and 1, which is the regular bit, binary bit, 0 or 1. A quantum bit, to give the game away, is not 0 or 1. It's kind of bit of 0, bit 1. So it's kind of probabilistic mix of 0 and 1. Okay. Remember, I told you that in classical physics, you know where the particle is. In quantum mechanics, you kind of have a probability of where it is. Likewise, you can think of classical bit as knowing exactly it's going to be 0, it's going to be 1, or it's going to be 0, or it's going to be 1. With quantum bit, now it's a little bit fuzzy. You don't know if it's 0 or 1. It has probability of being 1. It has a probability of being 0. Right? So there's that hazy bit. Now, this hazy bit will be resolved at the end, but for now, think of it as instead of head or tail, you think of it as a spinning coin. Okay? Because it is a spinning coin, you can't really implement it on a transistor the way we have the current technology. And that's why you have so many high-tech companies around the world right now trying to find out which way to represent this spinning quantum coin. Okay? Sometimes uses laser, sometimes use some kind of plasma or what, I don't know where the technology is. Okay? And nobody knows which technology is going to win now. It's like, you know, in the beginning of automobile, you didn't know if it was going to be a gas turbine, if it's going to be a internal combustion engine, if it's going to be electric, if it's going to be steam. It's kind of like you don't know what's going to power automobile yet. Okay, it's like that. Right now, nobody knows how to physically implement. Okay, that's what physical substrate means. The thing that implements the mathematical reality. Okay, so. Whereas right now, we have the technology to implement actual 0, actual 1, either 0 or 1 in a transistor form, which gets, you know, sort of like miniaturized into an array of 0 and 1, array of transistor, and that's your integrated circuit. Right now, nobody is sure which technology is gonna win. Okay. But probably not laser. I kind of heard that laser is a little bit unstable, a lot more unstable to work with or whatever. Anyway, so that's why I said, however it's implemented, because we don't know how exactly. So right now it's a question. When I say however here, it means however it's implemented, we don't know what it is. Okay. Now it's not going to perform. Remember 2 slides ago, it performs what? General purpose information processing. Quantum computing doesn't do that. It's performing search and optimization. It's a bit more specific for now anyway, okay? It's taking advantage of quantum phenomena called superposition. I'll talk about it later, okay? But this is something that is unavailable to classical computing. So just as classical computing has this layer of programming complexity, layers upon layers of programming complexity, that's not available to an adding machine. This quantum mechanics based bits, this quantum computing has capability of search and optimization that's definitely not available to classical computing. Okay, what do I mean by not available? It means that certain problem that a quantum computer can do in an hour would take supercomputer, the best supercomputer in the world, 5 times the ages of universe to solve. Okay. Now, you can ask, hey, how do we know that? Why don't we just make a computer faster? It has to do with scaling. And I'll teach you about scaling a little bit because you have to understand that. Actually, I can tell you right now. Okay, how many people, let's say there are 20 students in a room, okay? One of them has COVID, only one of them, okay? I can take ATK test and apply one by one, okay? It's possible that apply the ATK test to the first guy and right there, get the signals, right? Two little knots, right? So just one trial and I get my answer. You have COVID, okay? It's also possible, right, that the first one doesn't, try the second one doesn't, third one doesn't, fourth one doesn't, fifth one doesn't, all the way until the 19th one doesn't have COVID, then I know that the 20th one has COVID, right? So how, on average, maybe I can say that it takes me about 10 trials. I should be able to have the half 50-50 probability of uncovering, okay? The point is this. The point is, let's say at worst, 20 students, at worst, I take 19. Might as well test the last guy, so 20. So if n is equal to 20, how many steps do I take? 20 steps. Okay. If there are 100 students, what's the worst that can happen? Take 100 tests, right? So the size of the problem is n. The number of steps is also n. Okay, it may be 3n, 4n, but it's not n squared. Okay? Now, the whole thing about quantum computing is this. Some problem that takes a classical computer n step would take quantum computer square root of n step. Or some problem that would take classical computer n square step would take quantum computer n times log of n. This is called scaling. Now, you think it's not a big deal when n is equal to 2, when n is equal to 3, but when n is equal to 1,000, things get scary. And the problem is, some problem is so difficult, if the size of problem is n, it takes 2 to the power of n steps. Now think about it, okay? If n is equal to 10, 2 to the 10 is already 1,024. So it gets huge. And I'll skip to this slide just to show you the number, because I don't memorize it on top of my head. Where is that number? It's a big number. There it is. Okay? When n is equal to 50, the 2 to the n is, God, this is what? 1,000 trillion. That's a big number. It's a big number. Okay? So you can imagine that some problem is so big, it's not big. It scales up so fast. It scales up to the order of n squared. If a classical computer solved this using n squared step, but quantum computer solved this in, let's say, n log of n step. That's the difference between running the computer for 3 hours versus running the computer for 500 ages of the universe. Okay? And there, you can go to YouTube and see a lot of numerical demonstration of how big number gets, how fast the number gets. And that's what it means. When I say that it's not available to classical computer, it means certain problem scales so ridiculously fast like this. This is the, in practical purpose, this is probably the worst. Okay, for practical application, this is the worst. Okay, and this is not doable in any supercomputer, even if the computer is 1 million times faster than what we have today. It's not going to do it. Okay, so that's the promise. It's the scaling. It's all to do with scaling. It has nothing to do with anything else, just scaling. Conversely, it also means that when the problem is small, chances are a classical computer is faster than quantum computer. Actually, it's better. Okay? Because quantum computer is probabilistic. It's like saying, now I'm being ridiculous here, okay? But let's say that if you have some simple question, like f of x, and the answer is supposed to be 7.5, right? The quantum computer for that simple question will give you something that's most likely 7.5, but there's a probability it's 8. Okay, so for a very small problem, quantum computer is not better. Okay, but it's for the huge problem, it's a difference between doable and not doable. And that's why we hear the word quantum computer can crack RSA, which is cryptography. Okay, cryptography is not crackable under classical computing, it's crackable under quantum computing. Okay, given some, technological hurdle. Okay, so you understand where that is. Okay. Now, so this is a slide that I use just to emphasize the point. This is actually how the computer looks like in, I don't know, 1950. It's this room. It's the size of this room. Okay. Well, in terms of working principle, the mathematics behind it, this computer and the one in your iPhone is very similar. But this is much different from quantum computing, which is this guy. Okay. This is the one at IBM. I don't know if this is the one that they let the public use. I can tell you that I think around 2018, I'm pretty sure that was the year, or maybe a year before that, IBM made their quantum computer available to the public. It doesn't mean that I go to the computer at IBM and key in something. What it means is that I can send in my quantum computing algorithm to IBM portal, and they put it in a queue because this is open for everybody. And when the quantum computer is free, loads my program, execute it, and give me the result. Okay, I actually ran this. Yep. No. Oh, the queuing, yeah, definitely. I don't know if there is something more to it. From what I understand, this is very academic, so it's first come, first serve. But AI is no longer academic, so maybe you can pay more to cut the queues, I think. I'm pretty sure you can. Okay. With most AI as or on cloud as a service, I think there's some kind of like, premium pay structure where if you get a free version, you wait till everybody goes to bed. But if you pay a lot of money, that sort of thing. But as far as I know, this was purely academic for IBM. So it's like first come, first serve. Okay. I'm pretty sure there's nobody was making money from this yet. Okay. Right. So anyway, 5 years ago, exactly on my birthday, actually, I sent an instruction, quantum program instruction to IBM, and a few hours later, it didn't take that long to execute, but again, waited for the queue. I got the result back. Okay, but it was one of those hello world programs, nothing to write home about. Okay, but it was kind of fun, because I was sitting, I think at that time I was in the SEB at the bank. So from my little office in the bank, I executed a quantum program using real quantum computing machine. Okay, so let's go back. Okay, well, we'll be back here. So you see a lot of quantum here, okay? And there's a lot of nonsense, right? There's a lot of quantum fun, quantum this, quantum means nothing. Okay, it's like you guys boys, you shave, right? There's like a Gillette shaver, right? There's Gillette Turbo Plus. Okay, you can't turbocharge an shaving kit. It makes no sense. Okay, but you apply the word turbo to a razor, it makes no sense. Well, same thing here. People apply the word quantum to investment, or quantum to game, quantum gaming, quantum GPU. Nonsense. All nonsense. Okay. It just means hot stuff. It means nothing. Okay. By the way, this is what quantum mechanics at the lowest level. Remember, I told you guys about position being probabilistic. Well, the position of an electron is kind of like a 3D distribution. It's not online, right? I do a one-dimensional probability PDF. Well, this is like three-dimensional PDF. Okay, except they don't draw it as a curve, they draw it as a cloud of probability. And this thing, the difference between each of these is a jump in energy state. So from here, it's a low energy, this is the next higher, and so forth, right? That sort of thing. And as you go up, it goes up in step, and that's the quantum. But I don't know the details. I think this additional number of electrons or something. But I think it goes from for a given number of electrons, I think it's on the same row, and this is lowest, higher, 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 higher. Okay, I'm not quite sure. It's too small anyway. But anyway, that's the point. That's the point. This is a probability distribution of where you can find the electron. The quantum mechanics is not working on this one. It's working on the wave function that when square gives you this cloud. Okay, that's why it's called wave mechanics. Okay, wave function. Now, I'll give you something else, and this is also important. There is a second word of quantum computing, which is also legit, but it's not what we mean here. It's called quantum annealing. So when you hear things like a company like D-Wave has an 8-bit quantum machine, they don't mean quantum computing in the same way we talk about here. They mean quantum annealing. Now, I can take, because again, I'm not teaching quantum computing class here, I'm teaching emerging technology. So you might as well know about quantum annealing machine as well. What it means is this. You guys see this function? And this is completely intuitive. Just look at it, right? Let's say I want to minimize this function. Okay, you learn calculus, right? How do you minimize a function? You take the first derivative, set it equal to 0. But what else do you have to do? You have to check that the second derivative is positive, right? Now, if the second derivative is positive everywhere, when you first set the first derivative equal to 0, you at the bottom of the bowl. So that's the minimum, right? So if you have a bowl, there's one minimum. That's why you can set the first derivative to 0, check the second derivative is positive everywhere. You can do that. Okay, in multi-dimension, you use gradient and Jacobian or Hessian or whatever. Okay, but basically that's it. You just have one point at the bottom. Now imagine trying to minimize this function. Now this is something that you might as well learn now, because this is going to happen in machine learning as well. The idea is that somehow you want to get to the bottom. The lower, the better. The thing is, you can't solve it globally. You have to solve it locally. What do I mean by locally? I mean, I take an airplane, I fly over, and at some point, I jump off and I land. And based on where I land, I walk downhill. So obviously, there's a little bit of luck, right? If I happen to land here, I'm going to walk downhill and end up here. It's slow, right? And I'm pretty happy with myself, right? But actually, if I can call my friend who happened to land here and he walks down here, he's going to say, hey, I'm much lower than you. Okay? This is a competition to get to the bottom, right? So obviously, depending on where you are, I can get stuck because I'm walking downhill. Okay? This is called gradient descent. Gradient just means slow. Descent means go down the slope. So walking downhill just means gradient descent. Gradient descent algorithm is what drives virtually every AI machine today. There are alternatives, but you have to say that ultimately everything is based on gradient descent, walking downhill. You can think of this hill as minimizing error. So the lower, the better. Here's the problem. Well, you already saw the problem. If I start here, gradient descent, I get up here, but I want to go down there, right? So ideally, I should have walked uphill and then downhill. Okay? Walk up here. Well, here's a funny thing. I can build randomness into it. So instead of just walking downhill, there's certain probability I would walk uphill. So maybe if I just land just here, by luck, by chance, I can walk uphill. And when I go on downhill, I go on the other side. I get a better solution. Okay? This kind of going downhill, but occasionally going uphill, don't ask me why, it's called annealing. Okay? It's called annealing. If you have a friend who actually is in metallurgy or engineering, annealing is what happens when you take melted iron and let it sit. It's called annealing. Exact same word for exactly the same reason, but I don't have time to tell you why. Okay? Same thing that's happening to the metal structure is happening here. Okay? It's exact same word. In fact, their word came first. Annealing came from metallurgy. We borrowed that word because we're doing similar thing. Anyway, so that's why it's called quantum annealing machine. Just ignore if you get intuition later. Anyway, the point is this. The point is this thing is very common. Right here, I show you a picture of what's called a traveling salesman problem. And this is one of those problems that is, if you can solve this or some aspect of this problem, you can win $1 million. Literally, okay? They're like millionaire prize. $1 million will give you, if you solve this problem, there are about, I don't know, maybe 7 of them left. I don't know. Okay? One of them has to do with this. Okay? If you can prove something about this, you get $1 million from the Millennium Foundation or whatever. So it's not easy. Anyway, it's this kind of thing where if you plan to travel multiple cities, maybe this is the least amount of distance you can travel. But maybe the global best is here. So what you should do is somehow, maybe occasionally, jump over a peak. Okay, that's called annealing. Well, quantum annealing is pretty cool. And please, feel free to laugh. Imagine that this is a mountain. Yeah, and this mountain is like 5 kilometers thick. It's not likely you're going to jump over. Well, if you're going to jump over, it's the height, it's not the width, right? So imagine this mountain next to you is really thin like this. It's thin like this, okay? Say maybe a meter thick, okay? Not 500 meters, but 1 meter. How are you going to get on the other side? You still have to climb up this, right? Vertically, the same distance as if it's really thick. Well, here's a funny thing with quantum mechanics. Somehow, because it's working with probability, if this barrier is not that high, it's not that wide, the probability fall kind of creeps over. So it's possible that you go to bed over here, you wake up over here. It's called quantum tunneling. Okay? I can't tell you how that is. It's fact of life. Fact of life. Right now, you are here. I close the door. You can't get out. Right? You can't get out. I open the door about 5 centimeters. You can't get out either because you're bigger than that, right? You can't squeeze through. There's no way. But if instead of you being a definite position like classical physics, I make you a probabilistic location. There's a probability of you that leaks outside. And when somebody turn on the light, you're outside the door. Okay. So There's a probability of where you are, and there's exactly location when somebody turns on the light. With quantum physics, there's like two story, okay? Before you open the curtain and after you open the curtain. Okay. So that's why they have this thing called quantum tunneling. You can actually occasionally go through a thick wall and then go down here. And this is very important commercially. And that's why D-Wave is a very valuable company. It's not valuable to you. You know who is valuable to? What does this look like, guys? Logistic, right? You have to drive a truck or whatever, ships or whatever, and deliver goods in different cities, right? Amazon, for example, has to distribute goods in depot, right? And from depot, they have to distribute. This is all logistic. Okay? This is real. This is real. I'm not kidding you. We get lots of money to do this. Think of the ATM. Maybe right now you guys don't use ATM anymore, right? Because you got the thing. My bank had to pay a lot of money to build a model to determine the best route to fill the cash. Because each point here is a location of cash in Bangkok, right? Why do we need to minimize the distance time? Because we don't want to put in a lot of money in the ATM, because that's kind of like inventory of money, right? Money in ATM doesn't earn anything. So I want to put in as little money as I can in the ATM. But if I put in too little, what happened? Customer complain, right? So I have to optimize the filling route so that it takes a minimum time, so I don't have to put in a lot of money. Because as soon as it's low, I can fill it up in 5 minutes or whatever, 10 minutes. Okay, this is real. This is real. I knew the guy who was in charge of SCB's optimization. Later on, he moved to another bank, but this is real problem. He didn't use quantum D-Wave machine to solve it. He used other heuristic. Okay, but this is real. This is real. Okay, and this is it's just one slide, but this is also. It looks like a tangent to what we're doing. Okay. Now, we're also going to do the optimization, but not this kind of optimization. We're going to do kind of like a combinatorial search optimization. I'm going to skip a little bit of this to save time. Now, I'll just give you one thing. And this is see, it gets loud right away. Really good dramatic point. And this is a thing that you should learn. And I can't emphasize this enough. For those of you who keeps asking, when does this technology make money? Or how is this going to apply to real life problem? I can tell you that if not all, then virtually all the game-changing technology in your lifetime. I don't care if it's AI, I don't care if it's nanotechnology, I don't care if it's robotics, I don't care whatever technology, biochemistry, genomic, transcriptomic, I don't care whatever emerging technology you're talking about. I can tell you that none of them, or 99% of them, did not originate from a question, how can we make something that make money? It starts all as pure intellectual curiosity. All of it. All of it. Okay? And the timeline for quantum computing is probably here. This is Feynman's. So it's kind of rare, but you can actually put down the date. It's 1981. Okay? Richard Feynman is actually the most famous guy. You guys seen Oppenheimer? Well, Oppenheimer is kind of like previous generation of scientists, but actually, if you remember, there's a scene where they were testing the nuclear bomb, and one guy was sitting behind a truck. That's Richard Feynman. In another scene, you see a guy playing bongo. That's Richard Feynman. He was a very young guy back then, I guess. So, okay. So this was when he was a little bit older. Okay. But anyway, he wanted not to build the quantum computer to crack cryptography so he can make big bucks in the Bitcoin market. That was not his thing. That was not his thing. In fact, Bitcoin wasn't invented to be a market for speculation either, but that's for next week. He actually wanted to do the simple thing. He said, you should study the thing with the instrument on the same scale. Simple as that. Okay. So, if I'm going to study your muscle, I can use my hand. If I'm going to study your teeth, I need the dental instrument, which is a little bit smaller. If I'm going to study quantum mechanical physics, I need a computer of that scale. That's basically what he meant. Okay? So quantum computing was actually created to study quantum mechanics. It wasn't created to make money in Bitcoin. And again, this is the lesson I want you to take. A little, trivial innovation like, putting ketchup in a squeeze bottle. Yeah, you can say that those things start from people saying how I can make money from inventing something. But none of the game-changing innovation that affects your life, none of it was born out of commercial interest. It was all intellectual interest. And this is one of those. Okay, and this is kind of silly because this is 5 years ago. This is not true anymore. I didn't bother updating the slide. This is kind of like counting the Google search. And 5 years ago, quantum computing came in front of ChatGPT kind of search, like a chatbot, right? Nowadays, it's going to be the opposite. Now this thing is going to be like way off the chart. This was 2018 or something. Okay. Right. So before we get to quantum computing, again, I need to tell you about this thing. Now, I already told you that quantum mechanics, right, work on this thing called wave function. Wave function is a thing that gets knocked around, move. It's a thing that is the element of it's the quote-unquote variable of a differential equation. By the way, the most famous is the first one. It's called Schrodinger's equation. It's basically a partial differential equation on the wave function rather than on x. It's on phi of x. Okay? Oops. Show you what it looks like. Okay, whoops, sorry. Schrodinger equation. That's what it looks like. Okay, as simple as it gets. Okay. Okay, can you guys see this? You can see that this is a partial differential equation because it's partial derivative with respect to t, right? And instead of right now here being x, it's phi of t. Phi is kind of like a wave function as a function of time. There's also position implicit in there. Okay. There's I, imaginary number, there's Planck's constant, so all kind of funny stuff. But anyway, all you need to know is that it's a partial differential equation on the wave function itself. Okay, and that's why it's called phi. Okay, just as you have x of t, now you have phi of t. And that phi, again, is an abstract thing. You need to square it to get the probability, right? So that's what you need to know. Okay, so so you need to know that things behave funny at quantum scale. Quantum tunneling is what I was talking about. It's like this thing, that it can kind of like break through mountain. It's a little bit like tunneling, but not with the actual digging. It's just got to call quantum tunneling. Now, the other thing you need to know is called quantum superposition. And this is the most important thing today. It's the fact that, well, actually, there are two things important. Quantum tunneling is very important for the D wave that I was telling you about. Okay. For our class, this thing doesn't play too much of a role. This effect is really for the D-wave machine, quantum annealing. Okay. Now, for quantum computing that we deal with, is the bottom two aspects. One, quantum superposition. What it just simply means is that it's the probabilistic superposition of 1 and 0. Okay. So instead of saying that it's not 1 or 0, it has probability of being 1, it has probability of being 0. The word for it is, it right now is a superposition of 1 and 0. Okay. So in other words, when I talk about this quantum coin that's spinning, it could be head, it could be tail, right? Now with a quantum coin, if it's a literal coin, it's 50-50, right? It's 50-50. But you can have coin that's kind of like bent, so it can be 90-10 probability, right? It doesn't have to be 50-50. Well, that thing, when we talk about probability, it's PMF, right? Bernoulli distribution function, 0.9 head, 0.1, 10, 0.91, 0.1 or 10% probability of 0. Okay. Well, we don't say it that way. We say it's a superposition of two states, 0 or 1. That's what makes qubit different from ordinary bit. A deterministic ordinary bit is 0 or 1. It cannot be both. Quantum bit is also not both, but until you turn on the light, like you stop the computation, while it's doing this behind the scene dancing thing, before you open the curtain, before you turn on the light, it's kind of like superposition of 0 and 1. That's the principle. Okay? So 1 qubit is neither 0 or 1. It has probability of being 0, it has probability of being 1, but we don't say the word like that. We say it's a superposition of 1 and 0 state. But then, just like a coin, eventually when you clap or whenever it falls, eventually it becomes head or tail, right? That's like the end of quantum computation. Okay? At the end of quantum computation, the thing that was formerly mix of 0 and 1 has to stop. And it has to be 0 or 1. If you run this experiment again, stop, it may be 0. Guess what happened? If you run this 1,000 times, you're going to end up with 0 and 1 according to the same probability. Let me say that again. A quantum bit, okay? Look at me. A quantum bit, let's say I have this quantum bit spinning. And I tell you that this quantum bit has 0.6 probability of being head, 0.4 probability of being tail. The quantum bit is kind of like spinning because I haven't seen it. I open the door, I open the curtain, I turn on the light, I stop the computation, and that coin is going to go boom, head. The point of 0.6 and 0.4 is that if I did this 1,000 times, I should see number 1 around 600 times, give or take. I should see 0 about 400 times, give or take. Okay? And in fact, this is why I said to you earlier, quantum computer doesn't give you something definite, right? Now, if it gives you something with probability 0.6 and 0.4, you know, it's pretty risky, right? Hopefully, you design the experiment so that it gives you something with high probability that it's going to be in certain solution. Okay, so when I told you earlier that, you know, f of x is 7.5, with quantum computer, it could be 7.5 or it could be 8.2 with some probability. Well, hopefully you will program it so that the right answer comes up 99% of the time. Okay, that's what quantum algorithm is all about. Quantum computer is about maximizing the state probability that result in the right answer. That's very hard to understand. I'm sorry, guys. I can't make this easier. Yep.
So basically, quantum computing is like computing based on Possibility.
Yes. Probability, not possibility. Yeah. So if you did your programming wrong and the answer is 7.5, you run this quantum computation 1,000 times, maybe you will get 7.5 only 700 times. But if you program your computer right, your quantum computing, okay, quantum programming right, and you did this 1,000 times, that answer 7.5 would show up 997 times. And maybe 3 times it would show up 8.9 or something. Okay? Right? But it's not desperate, guys. But you remember, we're talking about the difference between doable and not at all. Right? So alternative is that, wouldn't it be nice to work with a classical computer because it's going to give you exactly 7.5? Well, for the problem that it can solve, yes. But for the problem I told you about earlier, there are many problems, interesting problems, it cannot do. So that's the best you can do, guys. So basically, you're going to end up, this is what the quantum computing result looks like. It's basically a histogram. And your answer is the one that has the tallest stick or tallest column. That's what you get. And in fact, you might remember I told you I sent a program from my bank, SCB, in 2018 to a quantum computer, 5-bit quantum computer somewhere in the United States. When I got back, there were 4 lines. There's a tiny line, there's a big line, there's a tiny line, and there's a tiny line, tiny bar chart. There's a small height, big height, small height, small height. And the answer is the big height. Okay? But because the program was written in a way that guarantees that this thing is going to stand out. And I'll show you how it works. I can show you with Mathematica to simulate exactly what it works. And that's the second half of the class. So let's see. So this is a good. Yeah, so I'm going to start. Okay. I'll make a final note. Quantum computing is not about keeping Moore's law going. Actually, what's happening, this is a side conversation, guys. You know about Moore's law, right? Right? Computers sort of like, the power of computing. So this is kind of like, I can't see it, my eye is not that great, but you can see that the size of the individual transistor gets smaller. This is a log scale, so it's not a linear function. Right. So now I think 7 nanometer is about where we were at 2019. I don't know where we are right now. 3? Okay. Well, you know what? What happened when we get to 1 nanometer? We're going to be in trouble. Because at that level, this thing that was my friend, our friend, starting to be our problem. Because now you can think of it this way. Remember I told you about you in this room, I open a small door, you can't get out, right? Well, think of an electron. If an electron is in this room, the transistor reads 1. If the electron goes to the other room, the transistor reads 0. Now, if I open the door a little bit and there's a quantum tunneling, I set this bit to 1. It goes to 0 randomly. So with the classical computer, you want to control the turning of 0 to 1, 1 to 0. You don't want it to happen randomly, right? Now, the point is that at 7 nanometer, it's like electrons is here and the door is huge. So it's not possible to jump, right? But once you get to like 1 nanometer, you can imagine that instead of a door, we can talk about a fence, right? It gets smaller and shorter, and right? So when it's a big wall, 7 nanometer high, electron can't tunnel over or jump or whatever. But when it gets so tiny, there's a possibility that a bit that was set to 1 just go to 0 randomly. Now, there's a lot of computer engineering that works with redundancy so that there's bit correction and all that stuff that I'm not talking about. But you can see why. As we get smaller and smaller, this quantum tunneling is not our friend. Okay, that's our enemy. Okay, you know what happened in silicon engineering? They're not just making the thing smaller. They're making the micro architecture more difficult to climb, basically. Right? Think of it as a wall that's 1 meter tall. You can jump easily, but what if you make it kind of like irregular or maybe with barbed wire? It's a little bit harder to jump, something like that. Or maybe it's slanted this way, so I can't get a foot, whatever. Okay, you see what I mean? So that engineering right now at the cutting edge of silicon engineering, it's not just about making it smaller, it's also about how you stack the transistor. Very advanced stuff, you know, way before anything I can understand and tell you about. Okay, so anyway, so that's the last. This is good. Hold on. Let me do this. Let me instead of giving you, I should give you this the slides rather than. Hold on, missing it. Okay, and then I'll show that. How do I play? How do I play this? Because it's GIF actually. There it is, guys. See this? This is what electron tunneling is all about. Okay. Remember the red line here can be negative because the wave function can be negative. Well, if you square this, you get the probability distribution. Now, because this wall is thin enough, the probability fall kind of leads to the other side. So there's a probability that electrons start here and kind of like tunnel through to there. That's called electron quantum tunneling. Okay. So this is just like a barrier. It hits the wall, but instead of like bouncing back. Now, if this was a classical, first of all, you wouldn't have probability distribution moving. You have a point. So a point would hit the wall, bounce back. Now, instead of a point, you have a wave traveling. But not only that, the wave go through the other side. This is what it looks like. See that? You can see faintly. Okay, this is okay. Let me show you. Okay, right now the electron is definitely on the left side. Hit the wall. There's a probability leaked over here. You can see a faint glow over here. So that if somebody turns on the light right now, stop the experiment, there's a finite probability that electron will end up on this side. That's like if the electron is over here, the bit is set to 1. If it's over here, it's set to 0. It's like because of this fluctuation, you set this into 1, and one day you come back, it's 0. And you didn't do anything. Okay? So it's kind of like ghost. Okay? You don't want that. This risk was not significant. 10 years ago, nobody cared. Because if this is electron, this thing is so big. This barrier is so big. But as you miniaturize, the barrier gets so small that you can successfully leak the probability. That's what it means. Okay? So, now when we come back, let's take a 5-minute break. I need a 5-minute break.